we know that the vector in the tangent space is the velocity of some curve. So please allow some curve here, map it, and differentiate to get the velocity vector. Let's please differentiate this equation from an engineering point of view. What do? Y dot equals what? We're differentiating with respect to time, the coordinate on the real for the curve. Y dot equals what?
Jacobian.
Very good. Partial f, partial x, right? The Jacobian at p, because I'm just interested at this point, times x dot. So this is indeed lives where? This is in the TPM, right? This is my v, possibly this is my v, and this lives where? T at
Pn.
f of p of
M.
n. Okay? So like I said, actually this is what I like to stress, is the language. We want to just want to be very comfortable with the language. I'm not promising anything else. Okay? Any question so far? So if f maps m to n, this guy, which is the Jacobian, it's nothing but the Jacobian evaluated at a point. Don't make it a big deal, okay? We just give it here a name in the language of differential geometry. It's called the tangent map of f. Okay? Sometimes, and actually most of the time, we call it push forward of f and denoted by f star. So f star or df is more representative, it's more expressive, I mean, because it's differential of f. F star is just the Jacobian evaluated at a point. So if f mapping points, f star maps vectors. So f star at p, we'll come to this later, f star particularly at p maps from where to where? F star maps from where to where?
TPM.
TPM, very good, to TF of p. And it's linear, the mapping is linear, okay? Remember, this is a vector space, this is a vector space, a linear map between vector space, you can always represent it by a matrix, right? Okay, it's a, if f is diffeomorphism, this is linear isomorphism, this is on the side. Any question? Any questions so far? So it's just a linear map between velocities. So points can be mapped highly non-linearly, but velocities will always map linearly. The velocities will always map linearly, okay? So, knowing that, let's have a more precise definition for...
Professor, one question.
Sure, please.
You're talking about y dot and x dot as living on the tangent spaces.
Yeah.
But you're naming them x and y's as you're doing with the r, m, and n.
In coordinates, yes. If you
So,
yeah.
but they actually live in the manifold, well, in the tangent space, right?
No,
So
this is their representation
so
in
it's just a
coordinates.
representation.
Yes.
Okay.
Yeah. Very good question. You know what's that? This line doesn't want to. Anyway, okay. Okay. That's okay. We need to have actually one more definition for this, or one more property of this tangent map or the push forward. Let's assume that I have a function here, f, right? Gives you to the real line. Last time we defined the pullback. I could pull back this f here by large f. Let's have it maybe g to prevent confusion. Okay, so this is g, a function, C infinity function on n. Last time we defined the pullback of little g under large f, which is this guy, simply. It's nothing fancy, it's simply g composed with f, right? If you compose g with f, so apply f first and then apply g. So this composition is a function on n. So this guy is C infinity m. Obviously, for this thing to be well defined, so so I have g C infinity n. I have V in the tangent space but of M, but I have a relation between them. For all this to be defined, I need this guy, it's a tangent, it's a velocity vector, to act on that guy. If it's in the same manifold, I can do it easily. They are not, but they are related. So I have two ways of doing it. What? This V, I can push it forward by F star to be a velocity vector here and then let it act on G directly, right? Or I can have V act on the pullback, G composed of F. The two roots must be the same, of course, for things to be well defined. So this is like a property for F star. Here it is. So G, we said G composed on F, G composed F, this lives in C infinity M, right? I can have V act on it, okay? This must be equal to F star can push V. Now this guy is T F of P N, right? So it can act directly on G. So this is like a property of the push forward, and a relation between push forward and pull back. Any question about that? So,
Can you repeat that again?
sure. What I'm saying is that from this diagram might be a little bit more clear. G is a function on the blue N. So I cannot have V act directly on it. To have V act on G, I have two ways. I can push forward V by F star, the Jacobian, to have it as a vector here and then act directly on G, or pull G back to have it as a function on M. How? By doing G composed with F. Now this is a function on M, and have V act on that composed function. This is this statement precisely, right? With this in mind, actually you can have a third way to compute directional derivative, and it's actually the easiest. So this is three. So you have 1 and 2. We have already 1 and 2. 1 in ambient space, 2 in coordinates, right? Any set of coordinates you like. 3 for directional derivative. So this 3 for directional derivative. What? I have here my manifold. I have the curve gamma of t. So this is 0. This is gamma prime of 0. And I have F we know the tangent vector here very easily. This is one-dimensional manifold, right? The tangent vector is simply d by dt, because remember, a tangent vector is what? Tangent vector is partial x1, partial xn. I just have one coordinate, so it's partial this coordinate, so no partial, it's just d by dt, okay? So this is the basis here, d by dt. So this is a manifold, this is a manifold. I have gamma, a map between two manifolds, like our F, large F in the previous example. So I can use gamma star to push forward d by dt to this guy. So gamma is a map between two manifolds, R and M. So gamma star will push forward, this is the Jacobian, so it will push forward the d by dt, this is acting on that guy at t equals 0. This will be gamma prime of 0 in the t gamma of 0 m, right? So now I can have gamma of 0 applied on F directly, or do it by this definition, which is d by dt of F composed with gamma at t equals 0. And this operation is actually very easy to do. Let's do it in our example that has been flowing with us. Reminding you our gamma was t over 2 square root something, 1 minus 5t squared over 4. The function was, I guess, x squared, y, and z squared, right? And we did, okay. And we did the directional derivative in a couple of ways, and you can do it in many ways. Actually, this might be the easiest. Just compose f with gamma, please. So this is what the first squared, the second, plus the third squared, right? Okay, t squared over 4. So this is t plus 1 minus t squared over 4. This is f composed with gamma. So now the result that you're looking for is simply d by dt for this guy at t equals 0, which is obviously 1/2. It's super simple. Okay? So I gave you 3 ways to compute directional derivatives. Ambient space, which we don't like, but it's one way if you have the ambient representation. Second, in coordinates, which is the standard. Third, you can go to the very elementary tangent vector in your real line, d by dt. Okay. Any questions so far?